Thank you, Dimitrios, for the invitation and for the introduction. And thank you also, Frederick, for joining us in this adventure of using AI techniques for your discipline. And I'm, let's say, really happy to be back here to the Institute of Advanced Studies from, let's say, the last time I was here, it was on March 2020, when I gave another interdisciplinary talk on responsible use of algorithmic decisions. So today, the objective of this talk is more an introductory lecture on the objectives of using AI in scientific discoveries and the current achievements and future challenges. So I will start my presentation. So back in '95, a young, let's say, engineer in General Electric in the US, with William Couldrich, was actually started investigating new materials for lamps, for lamps. Essentially, the carbon filament of the discovered by Edison was proved to be not energy optimal and was breaking all the time. So William actually, after several years of trials, then he discovered, especially trials with a new type, with a new, with wolframium, or in Latin, or tungsten in English, as a replacement of the carbon in the field. So after a lot of trials, then an accident happened. So the robe of the tungsten was actually felt inside liquid mercury that was falling down from the heat. Then this was the beginning of a new discovery, the discovery of the ductile tungsten, which actually have a higher melting point, and it was more flexible. So this kind of technology is actually used in our lamps until our days. So the artificial intelligence, so this kind of discoveries actually takes time. There is a lot of trial and error. It comes with a lot of chance, to find the right ingredients for the new materials. So these are the types of problems, or limitations of the traditional discovery process that AI is supposed to tackle. So by using AI, we are aiming to accelerate the full cycle of discovering new materials, from the design to the actual development, and then by minimizing the chance. Just to take an idea of the economic impact of this acceleration, currently, it is estimated that new material takes something from 10 to 20 years to be discovered, and will cost something between 10 and 100 millions of dollars. So actually, with AI, we would like to speed up the whole discovery process. To contextualize a bit our discussion, especially for the young students that attended either in person or remotely today's talks, let's take a look on the evolution of the scientific methods. So you will agree with me that actually until the middle or the dark age, science was mainly empirical. So imagine scientists like Galileo or Boyle trying to design observational experiments, control experiments, okay, in order to ground natural laws, okay, as the gravity, etc., etc. So it was a period where we elaborated a lot the way that our measurement techniques, okay, of different physical quantities. So then, okay, with the advent of the advances in mathematics and in formal reasoning, okay, theoretical approach was actually dominated the scientific discovery. So it is the period of the big physics discoveries, things with Newton, the Newton laws, Maxwell and Einstein, which actually offered unified theories that can interpret, okay, that can actually integrate a lot of the previous observational results in their domains. So these models will actually became, the idea was to have just compact formalisms that can explain a lot of observed phenomena. And then this kind of theoretical approach was quite attractive for that time, but started to create a gap between what you can formally model and what you can actually observe in reality. Just to give you an example, remember that the boson subparticles was first invented, conceived theoretically, and only the last 15 years we were able to observe them in the laboratory at CERN. So then the third paradigm that came up after the Second World War with the emergence of computers and programming. So here scientists were actually relying more and more on simulations to model complex phenomena as like climate behavior, climate behavior, or even molecular interactions, etc., etc. So there was actually a transition. Okay, these models was either analytically intractable or experimentally inaccessible, and using simulations were actually gave rise to new forms of scientific reasoning, including scenario testing, model-based inference, and most importantly, in silico experimentation, virtual experimentation. Then, okay, in the 21st century was actually seeing a new scientific paradigm to emerge, with it's based essentially on the large-scale discovery of data and of the analysis of this data. So this paradigm is aiming to unify the three previous one, and I will tell, and you can think that this paradigm has been started to be used by astronomers, where actually the discovery of the new planets is based more on the image analysis of the sky from the different more and more of high resolution telescopes all over the world. Okay, so what is important, this new paradigm? Essentially because it gives us the possibility, what is the integrative nature of this paradigm? So starting from a theoretical, we don't need anymore to start from a theoretical standpoint that could drive computation and experiments, but actually by taking the data of these two possible sources and analyze them, this high-dimensional data, by using machine learning techniques to discover patterns, we are aiming to create new hypotheses. So the challenge of this the main challenge of this new paradigm, data-driven paradigm in science, is actually generating a hypothesis, that requires further study. Okay, now, you will agree with me that as scientists, we are more or less motivated by a notion of progress of our society, and then we try to make discoveries that serve this society. Okay, nowadays things in my understanding becomes a bit more urgent given the multiple planetary crises that we are facing. There is no doubt that climate change, biodiversity loss, pollution are reshaping our environment at an alarming rate. So I believe that you agree with me that there is an urgent need to accelerate the transition to clean energy, to restore ecosystems, and to eliminate pollution at the source. So nowadays, given the tight dependencies that exist between these three types of crisis types, actually we need to conceive new materials. So at the core, let's say, of the changing paradigm that we need to put on the forward is actually design materials, with sustainable properties all over their life cycle. During the development with respect to the resources that need to be devoted for their construction, during life cycle, during their use for ensuring particular functionalities that are targeted by specific, let's say, application scenarios, or even at the end when they actually not used it anymore and need to be decomposed. So essentially to design materials, that satisfy an increasingly large number of structural, of chemical, or mechanical and another processing paradigms, joint optimization is needed. Okay, and then the question is, if we want to accelerate the discoveries in that direction, how we can accelerate, given that the scientific community, our size as a size, do not grow at the level of the actual societal needs. On the other hand, the volumes of the data that needs to be analyzed for scientific discoveries not cease to increase, and as well as the type of problems that are involved becomes more and more complex. On the other hand, we have to admit that we made tremendous progress in computing, in our computing infrastructure, and we have, let's say, more than 30 years of research in a wide variety of AI models and AI systems that could actually be used to speed up the scientific discovery process. So the question, and this is what I would like to explain next, is how AI could actually accelerate the scientific research. So, different flavors of AI could be injected at different stages of the well-known hypothetico-deductive paradigm of scientific discovery. For instance, generative AI models could be used to autonomously propose new hypotheses and expand the experimentation space virtually. Okay. Robotic labs could automate experimentation by bridging digital models and physical testing. Results of both physical or in silico experiments could be analyzed with a high degree of reliability by AI models and machine learning techniques in order to discover interesting patterns and correlations. But then, something that is related to the next talk by Michele, even the scientific knowledge, what we actually publish in scientific papers, could have a machine representation that will allow us actually to verify the discoveries and identify eventually gaps. This will actually bootstrap, okay, the formulation of new research questions based on the needs and the background and the gaps in the knowledge between what the literature knows and what we discover in our own experiments. All this is aiming essentially to extract, integrate, and reason with knowledge at very high scale, because this is the main challenge nowadays. So, to give you a taste, okay, just a taste of where AI could be actually used, okay, for what kind of materials, we can think that AI could help us to discover better batteries. It will help us to discover recyclable car tires. It will help us to build more efficient or see-through solar panels. It will also help us somehow, okay, to conceive techniques that can actually directly capture CO2 from the air and transform it eventually by a catalyst to something useful, as for instance fuel, okay, for the planes or for other devices. So, according to your opinion, AI is actually going just to speed up something that humans could discover if they have sufficient resources, including time and money, or we can go beyond what current human scientists with traditional methods could discover. This is an open question for the audience. Pay attention before actually answering one way or another. In my opinion, it will be, depending on the material, it will be both. Okay. We are actually asking from AI to do a task, okay, which is much more complex, okay, than the tasks we used to see on the web. Okay. All these LLMs, which are based on trillions of tokens that we spent and we worked with colleagues has done for more than 2 decades on web information. Okay, all this abundance of textual information is not there for scientific data. So we are asking from AI to compete the best scientists on the world, okay, although the main fuel of the AI is not there for that task, which actually means that we have to be clever on the flavors of the AI that we should use. And these are the few things that I would like to explain a bit more in the sequel. To ground my discussion on the main topic of LPPI, okay, I'm going to give some examples from polymer research. Okay, polymers, and I'm not the one that is going to insist on that, they are actually an important class of materials, okay, known for their exceptional versatility, okay, in numerous properties, including thermal, mechanical, optical, okay, dielectric, etc. So they are ubiquitous in our everyday life, okay, from the cars to the packaging, okay, to our houses or whatever else you want. But recently, okay, they become more and more used by advanced applications like medicine, okay, like electronics and fine chemistry. So depending on the polymer type that we, on the properties that we are interested, the available open source structural data may range from abundant, okay, to very severely limited. One of the first, I cannot point, isn't it? I can only go back and forth.
The light, the little.
The light. Okay, thank you. So one of the earliest, let's say, effort was on the polyinfo dataset, which actually compiled, okay, known from the literature, directly from the papers, polymers, essentially homomers and co-polymers, okay? And then this was real polymers, around 8,000 such type of polymers. This is a data source, okay, that is several heavily used in polymer research. Other sources is the PubChem, okay, which actually describe small organic compounds along with their biological activity. And this kind of polymers are mainly used in the drug industry. Or the GDB13, which actually it's also about small molecule compounds with up to 13 okay, atoms. Now, out of this, a space of hypothetical polymers is constructed. In that, I will detail the mechanism. So this space, okay, for instance, here, in this example, the idea is to, I'm really sorry for that. The idea is actually to conceive new polymers whose the glass temperature that you can see here, okay, is really high. It's above 200 degrees of Kelvin. Remember, I'm not going to, that the glass temperature is the temperature at which the amorphous polymer transition from a hard glassy state to a rubbery state or vice versa, okay? So the whole idea is that the hypothetical structures that you can see here have proposed actually polymers that are estimated to have, okay, a glass temperature higher than a certain threshold compared to the green one, which are the known structures, or the yellow ones. Okay, so this kind of polymers, okay, are actually hypothetical polymers are actually constructed in the traditional way by error and trial by a manual process, or they can be actually assembled, okay, by building blocks, by components that we found on other on existing data sets, or that can actually assemble it, okay, by components and non-polymerization reactions. And finally, and this is what I'm going to detail in few slides from now, okay, is constructing the space of hypothetical polymers using generative AI technology. So here, what I want to stress is that hypothetical nanomaterial-based polymers and their composites are investigated in various applications related to storage energy and to storage production, and things like conductive polymers, okay, seems to be of particular interest in that respect. Now, we saw that we start expanding our design spaces with hypothetical polymers that have not been actually not all of the time constructed physically in the laboratory environment. Okay, so actually designing these hypothetical polymers is the subject of two different, let's say, complementary processes known as forward design, okay? If I learn to use it properly, forward design, which is actually the manual construction of the hypothetical polymers, so mapping the structure, okay, to particular properties, or of starting from their properties and then going back to the molecules. This is the forward and backward phases in polymer design. So what I want to stress is the following, is that revealing the coupling mechanisms between the structures and the properties of all materials, in that case of polymers, is a key step towards the design of new materials with controllable performance and programmable functions. In the case of the polymers that I mentioned previously, okay, if we focus on the glass temperature, then predicting this temperature from the data is quite challenging due to the complexity of the structure property relationships and the wide variety of the polymer chemistries. So here, either we start with a hypothetical space constructed by one of the methods that we saw previously, and then we try to essentially to screen which of these hypothetical models, hypothetical polymers, okay, will exhibit, okay, the desired properties. And this kind of job, which is known as high throughput virtual screening, relies on machine learning models, call it surrogate models. So the main idea is the following. The properties are actually of the polymers are determined by the atoms that are actually composing these polymers. So the mapping between structure and properties could be easily imitated by a machine learning model. Of course, it depends on the properties, okay, as we will see, and it depends also on the way that the molecules are represented. So, but we can do a better job rather than having already a hypothetical space that we filter out, of polymers that we filter out, If we have sufficient data, we can learn actually a probabilistic distribution of structures with actually desired, with properties of interest. By learning such distribution, we are able to generate de novo polymers, okay, without even needing to enumerate or possible hypothetical polymers. So the bottleneck of these methods for actually inverse design, okay, first of all, property-driven inverse design and structural property modeling are actually they are actually transforming, okay, the way that polymers are designed nowadays. So the quality, essentially, of the precision, the accuracy of the predictions that they made these models actually depends on the amount and of the quality of the data that we are using. And in that respect, okay, I will first zoom out on how we can represent within an AI program a molecule, the structure of a molecule. So, on one of the earliest attempts was actually to represent the structure of the molecules using hash vectors. Essentially, you have either counts or Boolean variables that indicate that particularly substructures are present in that molecule. Okay, this is a rather, I would say, tabular representation of the information. Then later on, we started representing molecules as sequences, as strings, which give birth to a number of formats widely used nowadays in computational chemistry, like SMILE. Okay. Now, molecular fingerprinting was actually heavily exploited for the so-called quantitative structural property models, relationships models, for screening. Well, string-based representations, without any surprise, okay, started to bootstrap unsupervised vectorial representations of our molecules using AI technology similar to what we are using for texts. So molecules are strings, and we build very performant models for understanding strings. Later on, and this will be the subsequent focus of my talk, rather than making an intermediate representation of the molecules as molecular fingerprinting or fingerprints or strings, molecules are actually by nature graph structured data, okay, where nodes are the atoms and edges are the bones. And this graph representation can be directly exploited in our days by the new wave in neural networks, which is known to be graph neural networks. Before giving you more details about that, I'm just illustrating here two large language models used for polymer strings, essentially constructed out of SMILEs. As you can see here, any kind of advanced architecture that we are using for representing text as bidirectional, essentially, embeddings or transformers has been leveraged in the context of materials and polymers. Now, we saw that polymers exhibit a graph structure. Okay. So now, GNNs are supposed to understand essentially directly the graph structural data and to represent it in a sophisticated way. The main idea of GNNs is actually the fact that the vectorial representation of your information compounds, of your nodes, could take into account local information. So actually, GNNs are built using a message passing mechanism that allow us to pass information, for instance, from a node, from a source node to a destination, okay, as you can see here, from 3 to 2 or from 5 to 2, then aggregate for node 2 all information from all the neighbors for 1, okay, for 3, or for 1, for 3, or for 5, and then update the representation of the node, okay, with information coming from the neighborhood nodes. So the way actually that the function, the way that we update and aggregate, okay, local information defines the exact GNN architecture that we are using. We can think about a linear, essentially capturing linear dependencies of nodes from their neighborhoods if we are using convolutional networks, injecting a bit of attention, learning the weights, okay, that we should pay attention to our neighborhoods, or in graph attention networks, or even having nonlinear combinations in message passing neural networks. So the GNNs have been heavily used for modeling a wide range of polymer properties, including thermophysical, as glass transition temperature, the melting point, solubility, density, okay, but also performance-related attributes like the dielectric constant, the mechanical strength, permeability, viscosity, etc., etc. These GNNs have been used in a lot of specialized domains, and they have proven that their ability to generalize well across diverse polymers classes, learning transferable chemical representations that outperform traditional shallow, I will say, or simply neural network approach. Now, I explained the advantages. There are also some downsides, okay? So the way that GNNs capture local information, and then it is related, okay, to how local is the information. This is the one hop nodes of one hop for this one, two hop, and so on and so forth, is done by introducing layers of latent information representation, okay? So unlike traditional neural networks, where adding more layers is supposing, okay, it will make the computations heavier, but you expect to improve performance. Here we will not observe, okay, this always this beneficial behavior. As a matter of fact, okay, deeper GNNs have the tendency to oversmooth the features, leading to uninformative node representations. While shallow GNNs, of course, they suffer from the inverse problem. The signals from the distance nodes are not ending up in their representation. And also other problems like sensitivity to adversarial perturbations or even how GNNs can represent graphs where they exhibit diverse neighborhood patterns, in particularly neighbors of a specific node do not share the same necessarily the same property or the same label. They are heterophilic. So to overcome these limitations, some recent GNN frameworks have been introduced, in particular graph neural diffusion networks. So what is the idea? The idea is that instead of several layers of messages passing on a graph, this framework considers a continuous time physical process on some domain. The domain could be a continuous manifold, which can be discretized as a graph. So the process is controllable by a set of parameters representing the properties of the underlying physical system and replace the learnable weights of the message passing layers of traditional architectures. You can think here, okay, that nodes in our graph under this perspective of a continuous process that is discretized okay, in across time, okay, you can think that nodes in my graph are nothing else than locations on our continuous manifold, okay, that the vectorial representations, okay, the vectors, the embeddings we create for that node at a particular time is actually the heat signals of that nodes in the manifold, and that across time these heat signals evolve, okay, and how they evolve on a particular timestamp, this is controlled by the way that the nodes in the positions in our manifold interact, okay. So in essence, we can represent the heat flux of the in that framework as actually a divergence operator where heat is actually diffused from one node to the other nodes at a particular timestamp, and then this diffusion is controlled by that factor which is called the diffusability. To capture uncertainties, the stochastic nature of the interactions between the nodes at different locations at a particular timestamp, actually this diffusability is not a factor, is considered to be drawn, okay, by a stochastic process, okay, for a particular, depending on the node and on the type, and then this kind of stochastic process will take several, we could inject several different types of prior knowledge, okay, which will make our network physics informed, okay. For example, we may consider, okay, either isotopic or anisotopic diffusion among the nodes in the graph. So anisotopic depends also by the location and the heat flux, the direction of the heat flux, etc., etc. So we can start, okay, modeling, okay, our physical world via a neural network that is could be aware of the physics that are involved for our physical problem. So note that given that the diffusability is actually a stochastic parameter, then makes the whole trajectory across time, okay, stochastic. So now we see I'm always confusing the front with the rear. Okay. Now, this type of models that I have presented you previously aim to solve essentially virtual high throughput virtual screening. And what about the pure inverse design methods? I could tell you that a lot of models have been produced that they are actually using, okay, almost all core techniques for generating generative techniques that have been proposed for image or for video data, for unstructured data modalities. Among this, I'm not going to make you a survey of all the different possible models. I will just mention that models like the reinvent that combines, okay, essentially that are based on reinforcement learning, okay, are proven to be most effective for generating de novo molecules. As a matter of fact, according to the empirical analysis of that work that I'm citing, okay, reinvent, given that I have a reasonably amount of data, then the reinvent can be used, okay, to produce molecules with could have a significant size and could involve different types of atoms compared to other methods. So a last observation on that part is that although a lot of different deep generative models has been used, what is missing from that picture is the diffusion networks, which is the most, let's say, recent advance in that area. And this is the topic that we are aiming to study with Guillaume and Salah during his PhD thesis. Now, please note that polymer informatics, okay, is not anymore a subject of specialized communities, communities of chemists, etc., etc. Challenges, okay, for building models that predict properties of polymers, hackathons, if you like, challenges, are present in mainstream artificial intelligence conference like NeurIPS. And this is the challenge from last year, the last year event. Okay, so here it is interesting, and this is a suggestion for Salah, to take a look on the winning solutions of these competitions and see the architectural characteristics of this of the winning solutions as baselines for what we are planning to do. Then we don't have only challenges at regular rates. We started really offering in the community using a wide range of methods, really large data sets. Okay, here the recently released Open Polymer 26 data set contains 1 million of hypothetical polymer structures and has been developed by the Lawrence laboratory in California in collaboration with Meta. So I didn't have the time to take an exhaustive look for which types of polymers that is mentioned. We have more of the examples, But it will be interesting, for instance, to learn the interesting properties over these data samples from these data sets and see how we can, if we can transfer it to more specialized types of polymers that are of interest for you. Now, I tried to present you the good aspects of AI, the success stories, okay? But there are a number of issues that AI cannot do. First of all, deciding what is important is inherently a multi-objective optimization problem, okay? So AI could help us in studying trade-offs, give a bit of that in order to take a bit of that, okay? But the ultimate decision remains human. Second, we have AI cannot convict humans, scientists, okay, to spend 3 or 4 years of their life, okay, in the study of particular hypothetical polymers that could exhibit the desired properties. So domain experts remain dispose strong intuitions and reasoning. They spend their entire life for developing them, okay? And they also have free will to decide, okay, if they are going to work in a particular project or not, which actually demonstrates the limits of AI. So AI remains purely on the digital space. Here we're talking about materials. We are not talking about consuming information. We have to fabricate, we have to construct these materials, okay? And as a matter of fact, okay, we need to test these materials under operating conditions. Consider, for instance, the case of a sustainable cement, okay? So AI could not tell us, okay, besides the in-lab laboratory that could can be conducted, how, okay, the cement will behave not in the small quantities that we test in the lab, but in megatons. Okay. Then AI is subject, okay, of let's say hallucinating predictions, especially when we push them, okay, to extrapolate. When we asking things that goes beyond the distributional characteristics of the data on which it has been trained. As a matter of fact, we can obtain from a generative AI model molecules that cannot chemically exist. So it is a question then how we inject, okay, this synthetic feasibility of materials inside the models that we are learning and there are that we develop, and there are few works in that direction. So actually, we cannot for the moment bypass the dominant presence of human scientists in the whole project. And the only thing that we can promise, okay, is a nice AI human scientific collaboration. But this brings us to the next topic, how this collaboration could be trustworthy or informative. And then I'm going back to my initial slides. Remember a bit how things, the different scientific paradigms. We started with observational. Here is an example from astronomy, okay, of Tycho Brahe, okay, in the dark ages. Then Kepler came later on, okay. student of Tycho Brahe, and posted, formalized it, okay, in terms of theories, or laws, okay, the observations about the planetary movement of his advisor. And then we got the third law of the planetary motion, which actually says that the square of the time to complete the orbit is proportional to the cube of the semi-length of the major axis. But what Newton offered was a unifying, essentially, theory, okay, that the Newton's law of the universal gravitation actually explained that this proportion here is because of the gravitational function, where M1 and M2 are the masses of the two planets, and R is the distance from the center of these two masses, and this is just the gravitational power. So, going back in our terms, in today physics terms, okay, this is about observation, this is about analysis, and this is about explanation. These three different evolutions in scientific thinking. So observations nowadays, okay, are commodified. We have an increased sophisticated technology to generate data for everything, okay. Then all the modeling efforts, okay, with different waves of artificial intelligence offer us a lot of different models to do our predictions. And what I'm arguing is that what is missing is actually explaining these predictions. If we believe that we are going to be based on models to do artificial intelligence models to do our research. So these explanations were actually aimed to open the black box of our predictions. The more we sophisticate our neural architectures to increase performance, the more we make opaque, okay, the way the model learned, okay, some critical characteristics that drive it, the prediction of interest. So by developing explainable AI, only by developing explainable AI, we will be able to move from a hypothesis-centric paradigm, as we see it until now, to a hypothesis-free paradigm where actually explanations could help, okay, scientists in generating in understanding new hypotheses driven by a data analysis, okay. So this is aligned, okay, a bit with the current evolution in terms of AI models, okay. We are making more and more complex models, okay, in particularly models not only for one property or not only for one type of material. We are making big so-called foundational models that can cover different needs, okay. So these models can be actually, these models will allow us to pass from not simply using AI as a tool for the different tasks, okay, ranging from literature search to analysis, okay, to protocol drafting and result insights, but to making, to construct a collaborative systems and then establish a scientist to AI agent communication that will actually help in designing the experiments and in exploring a wider hypothesis space, or even in paper writing, which will be the subject, of Michele talk after in a couple of seconds, of minutes. Okay, so this the long-term vision for foundational models, is actually to be the center of the scientific discovering process, making scientific discovery more and more autonomous from the human scientists. At that point, that a couple of years ago, was stated as not as a joke, but as a hypothesis, in the public debate, whether an AAA agent will obtain in middle terms, the Nobel Prize. This was raised for the first time 3 years ago, if I'm not wrong, in a conference in Japan. So, according to this autonomous scientific discovery, we started designing so-called self-driving laboratories, self-driving from the analog of self-driving cars, which combines experimental planning, device scheduling, data analysis, to scientist interactions, and a lot of computing infrastructure for storing and for making calculations. This was the part of the issues that we discussed last week in Tampere, in Finland, in the workshop XAI for Science. We organized it this year. And you can take a look on this website for some of the works. So in the context of this workshop, a preliminary work by my colleague Guillaume Brenton and by Salah Rizgi, I planned to include it to take a test, and I will first ask questions, and then we can ask our PhD student to give a taste on the explanations that we can construct. Thank you for your attention.